Everybody, let's finish up our study of static electricity by working some examples. All right, here's our first one. We have a particle A and B that place a small distance apart as shown in the figure. Describe the motion of the two particles when they're released and free to move. Explain why one particle will travel faster than the other, and explain how conservation of energy limits the final velocity of the two particles. This is a problem where we're going to have to use both conservation of energy and conservation of momentum. All right, well, these two particles are both negative, so therefore they're going to repel each other, and so they will get an electric force away, and so these two will accelerate away from each other. That's the answer to part A. By the way, this electric force, even though they have a different size of charge, they will have the same exact magnitude of force, one to the right, one to the left, as they repel each other. All right, second part says explain why one particle will move faster than the other. Well, they don't have the same mass. So particle A is 4 times the mass of particle B. So if we want, we can explain that with acceleration is proportional to the sum of the forces over m, or acceleration is just proportional to 1 over m since the force is the same. One of them is 4 times the mass, so it'll have 1/4 the acceleration of the other. That's one way to think about it. Another way to think about it is conservation of momentum. At the beginning, these particles are at rest. They have an initial momentum that is 0. And so the final momentum must also be 0. So we have mv for particle A, plus we have mv for particle B after they push each other apart. And since the mass of particle A is 4 times the mass of particle B, so we have 4 times mass B, VA equals, plus VB. This cancels, and we end up with the fact that the velocity of B will equal 4 times the velocity of A at the end. Our last one says, explain how conservation of energy limits how fast these two will eventually go. Think about it for a second. We have a certain amount of electric potential energy built up. It's actually K QQ over R, and so that will be a negative Q and a negative 4Q over X. So that's 4, positive 4, K Q squared over X. That's the amount of energy we begin with. For our system, that's all the energy we're ever going to have. So this will end up being the kinetic energy of both at the end, kinetic energy of A plus the kinetic energy of B. And we can put in 1/2 mv squared if we'd like for both of these and plug in what these velocities differences will be using conservation momentum if we like. But the key thing is we only have so much potential at the beginning, so we'll have a limited amount of kinetic at the end, and it's going to be split between the two. In fact, the funny thing is if we hold one of these in place and just release the other one, it'll actually go faster because all of the kinetic energy will just go into one of the particles instead of both. All right, here's question number 2. And again, we're going to be talking about conservation of energy and conservation of momentum. Read through this one, see if you can figure it out, pause the video, and then we'll work it out together. Now, it asks, using conservation of momentum, explain the direction of the stationary electron, which way it moves after the collision. All right, so this is conservation of momentum. Momentum 1 must equal momentum 2, but we have 2 dimensions going on. So we have an x original and we have a y original. I want you to notice that the y momentum originally right here is 0. All we start off with is a momentum in the x direction. So therefore, this is 0, so the final must be 0. Hey, that means that this particle that collides and moves off this way ends up with both an x and a y momentum. Momentum x, momentum y. Well, we can't have any y at the end. So what we have to do is have some y momentum in the negative direction for this one to cancel out. So this momentum cancels out this momentum. These two x momentums right here add up to the original, and so that's why this particle goes down and to the right. Okay, what about using conservation of energy to explain what happens to the velocity of the fired electron? So this one is moving along with some kinetic energy. It hits this one. Now, since this is an elastic collision, therefore, the kinetic energy we start with must equal the kinetic energy we end with. Now, the fired one has all of the kinetic energy at the beginning. But this one has some kinetic energy afterwards. So therefore, this one must lose kinetic energy and it has to slow down. So it turns up and to the right, and it also slows down when this one takes off down and to the right. Question number 3. We have 3-point charges placed at the ends of an equilateral triangle. Read this question, see if you can figure out the answers, and then we'll work it together. Okay, we have 3-point charges on this one. And we got a couple positives and a negative. And this one moves down here to point M. And the question is does it take work to move it down here? Or does it move down by itself and gain kinetic energy? So work will equal the change in electric potential energy if we have to move it down here. So let's find out what the change in electric potential energy is. So at the beginning, the initial electric potential energy will be the energy of this pair plus this pair plus this pair. Okay, so luckily the geometry is nice and simple. Remember that electric potential energy is K Q1 Q2 over R squared. And so what we end up with here for this pair is a negative K Q squared over D. And then this one is the same. Negative KQ squared over D. And this one is the same except it's positive, KQ squared over D, for grand total, because these two cancel, of negative KQ squared over D. Now let's look at when this charge is down here, negative Q, what's our potential energy now in the final position? Well, you see this outer pair out here? That's the same as it was before, KQ squared over D, because they didn't move. But this pair right here now has a new distance, D divided by 2. So this pair right here will have a KQ squared negative, because we have a negative charge, over D divided by 2, which gives us a D here and a 2 in the numerator. And this one, this pair is going to be the same, minus 2KQ squared over D. When we add all of that up, what do we get? Well, that's 4 negatives and 1 positive. So it's going to be negative 3KQ squared over D. So what does that tell us? So our potential energy was this number. Now our potential energy is this number. This number is more negative than the original. It's gone down in potential energy. So our electric potential energy equals our change in electric potential energy equals the final minus the initial. So we get negative 2KQ squared over D with a decrease in potential energy. That means this was a natural process and the potential energy turned into kinetic. So our final kinetic energy of this particle as it moves down here would be negative 2KQ squared over D, because this turns into that. Now, let's see if that makes sense. Let's look at it in terms of forces. This is a positive charge, this is a negative charge, so it will be pulled this way. Positive, negative, this one will be pulled this way. So yes, indeed, we get a net force downward, and it's going to naturally move this direction. It won't require any work to place this here. It's going to naturally move there by itself and pick up kinetic energy along the way. Oops, I did a dumb thing here. Kinetic energy can't be negative. Remember that the kinetic energy equals the negative change in electric potential energy. So it's the opposite sign of this, and the kinetic energy is positive. Almost broke physics. Number 4, we got points A, B, and C. They're located at the center of these square arrangements of charges. Calculate the electric potential at each one of these points. How much work does it take to move a proton from very far away to each one of these points? And part C, an electron is placed at point B and released. What direction will it move? Okay, first off, remember that the electric potential V equals KQ over R for point charges. and we have point charges here. Let's do this. Let's call this distance between here and here r to make life simple. And so the potential at point A from this one will be k q over r. Let's just call that v. It's going to be a positive v. Now look, this one's going to give me a positive v as well. This one's same geometry is going to give me a negative v and a negative v. So when you add all those up, the electric potential at point A is going to be 0 because they're going to cancel out. All right, let's look at point B, and I have the same sort of thing. I got a plus v and a plus v and a minus v and a minus v. So this one will also be 0. Now let's look at our last one over here on the right. I'm going to have a plus v, a plus v, a plus v, and a minus v. So these two will cancel. I'll end up with a plus 2vc, which equals 2kq over r, where this distance is r. And we can do the geometry if we need to find out what that is in terms of d. That's actually what? D divided by the square root of 2. How much work does it take to move a proton from far away to each point? Well, the work equals how much the potential energy changes. Remember that the potential energy far away equals 0. So if I go from 0 to 0, so the work for A will be 0. The work for B will be 0 to take a charge, a proton, and place it right here. How about for this one? Well, the work for C will equal delta potential energy, which equals delta V times Q, and our delta V is from 0 to this. So it's going to be 2kq over r times the charge, and it's a proton, so that would be E. And that's our work done to move a proton from very far away to point C. Now our last one says we place an electron at point B, so there's an electron at point B. Which direction will it move? All right, well, electron is attracted to this one, attracted to this one, repelled by that one, and repelled by that one. So those all add up to give us to the left. So it's going to move to the left. Okay, question number 5. This time we have a capacitor and our electric field. Read this question, work out the problem, and then we'll work it out together. Here we have 3 electrons at A, B, and C. They're electrons, so they're negative. Inside this capacitor, first question is which plate has the highest electric potential? Well, electric field always points away from positive and towards negative, so this must be the positive plate on the left, and this must be the negative plate on the right. So the highest potential will be the plate on the left. Which electron receives the greatest force? Justify your answer. Well, remember that inside of an electric field, as long as you're not close to the edges, the electric field is constant. So the charges are all the same size, and the electric field's all the same size. And so the force is equal to EQ, and these are the same, so they're all the same. Which electron will have the greatest velocity when it collides with the capacitor plate? Now, which way are these electrons going to go? Well, they're electrons, so they have a negative charge. So they get a force in the opposite direction of the electric field. So they're all going to be forced to the left. They all get the same force, but they don't all move the same distance. So now it says explain your answer using the electron as our system. So if the electron itself is our system, then all the forces on it will be external forces. The velocity will be related to the kinetic energy, which is related to how much work is done on the electron. And the work equals the electric force times the distance. We've already established that the electric force EQ is the same. They don't all move the same distance. So the one that moves the greatest distance will go the fastest due to the work from the external electric field. And that will be C, will move the largest distance from here to here. Now our next one says explain the same thing, but this time use the electron and the capacitor as a system as a whole. Now if we do that, then the forces between the capacitor and the electrons are internal forces. So we can't use this external work anymore. So what we're going to do this time is talk about the energy. So the electron starts with electric potential energy and it turns into kinetic. So the electric potential energy turns into kinetic. And remember, this is delta, or how much this changes, is delta V times Q. The charge is the same for each one. They're all electrons, but the delta V will be different. So if we take a look here, remember that our equipotentials are perpendicular and that our electric field always points from higher to lower potential. And this is going to be the greatest potential because it moves the greatest distance through more equipotential lines. So again, our answer would be C, because it has a greater voltage change for the same charge. Therefore, it'll have a greater potential energy drop, therefore a greater kinetic energy gain. Okay, 3-point charges produce electric field vectors as shown in this diagram. What are the signs of each of these charges? Which location has the highest electric potential, A or B? And sketch an isoline of constant electric potential that passes through point A. All right, work that one out, and then we'll do it together. Here we have 3-point charges that produce this electric field. What are the sign of each of the charges? Well, remember, the electric field points away from positives, so number 1 must be positive, number 3 must be positive, and number 2 must be negative. So there we go. Which location has the highest electric potential, A or B? Well, there's a couple of ways to figure this one out. Notice that this one is closer to the plus, so it has to have a higher potential. This one is closer to the negative or farther away from the plus, so it has to have a lower potential. So our answer would be A has the highest potential. You could also think of it in terms of isolines, but they're kind of hard to see drawing them all on here. So we've already got the answer. Now it does say to sketch one isoline, one that passes through A. Now remember that our isolines are always perpendicular to the electric field. So the electric field is kind of to the right here, and then up here it's a little bit up and to the right, and then it's like up and to the right more, and then it's mostly vertical, and then it's up and to the left, and then over here it's to the left, and here it's down and to the left, and here it's down, and here it's down and to the right. And so I drew perpendicular lines that kind of matched up, so this would be what my isoline would look like when we connect it all together. All right, question number 7. 3-point charges produce electric equipotential lines as shown in this diagram. What are the signs of each of these charges, and how did you come to that conclusion? What's the relative magnitude of these 3 charges, and justify your claim? Rank the strength of the electric fields at point A, B, and C, and sketch the direction of the electric field at those 3 points as well. And first question is, what are the signs of the 3 charges? Well, this is negative isolines around here, negative potential, and that's positive potential. So this must be the positive, and these 2 must be negative. We can see that these have to be the same sign charge because they are both enveloped by the same loops. If they're opposite sign charges, they will never be enveloped by the same loop. There'll be a dividing line between them that would be the 0-volt line. All right, what is the relative magnitude of the 3 charges? Well, if you take a look, you can see that this distance away, it's negative 20. This distance away, same, it's negative 20. And that same equivalent distance away, you see positive 10. So in part B, it looks like the negative charges have a greater magnitude than the positive charge does. But it looks like these 2 have to be the same. Okay, rank the strength of the electric fields at points A, B, and C. The electric field is related to the gradient, or the change in electric potential with distance or location. So I want you to notice that the faster that the potential changes for the same distance, the bigger the electric field. So right here, notice we have a lot of lines packed together. So the electric field here at B must be bigger than the electric field at A, which is bigger than the electric field at C, because the electric field at C, the isolines are spaced much farther apart. D, sketch the direction of the electric field at points A, B, and C. Remember, the electric field always points towards decreasing potential. positive over here, negative over here, so the electric field would point this way. Positive here, less positive over here, and so it goes this direction for our electric field. And then this one, negative over here, less negative, or more positive over here, so it's going to point this direction. Notice I've drawn my electric field vectors perpendicular in each case to the ISO lines. All right, yikes, I drew my electric field in the wrong direction here. So I'm going from negative to less negative, and so remember electric field points towards more negative, so this one is incorrect. It should be in the opposite direction. Let me fix that up for you. It should be in this direction, towards the negative. Okay, here's one that's a little different, but it has shown up on the AP exam. We have two charges fixed to the axis as shown above right here, negative Q and, a positive Q and a negative Q. Calculate the electric field and electric potential at the origin. And now sketch the electric field strength on the axis below, assuming that to the right is positive. So sketch the electric field here, and then sketch the electric potential on this axis. So we have a positive charge here, positive. And it's going to have an electric field that points away. So here it points away from itself here, it points away from itself here, and it points away over here, but it gets smaller as we get farther away. And then here is a negative charge. It's twice as big, so it's going to point in toward itself, electric field. And then over here it's going to point towards itself, but it will be bigger than this one for the same location. And then it will point in towards itself over here, but it gets smaller. So it's a possibility these could be the same size over here on the right. It says calculate the electric field and the electric potential at the center or the origin. Well, let's do electric field first. The electric field is KQ over R squared. So let's do this one first. That's going to equal K little q over X, and it's to the left. Hey, and this will add up, so I can just make them both positive. Plus this one is going to be K negative 2Q over X for a grand total of, not negative, we do the absolute sign. I almost made the same mistake all my students make. These two, we already know that they're going to be in the same direction, so I've already made them both positive in this equation just to find the magnitude. And so I end up with 3KQ over X squared. Boy, I'm making all kinds of mistakes. It's time to go to bed. And that is my electric field, and it's to the left. Now, electric potential is easier. It's a scalar. So this time, I don't want to take the absolute value. I just want to plug in the numbers as they are, plus and minus. Just add it all up at the end. So the electric potential from this one will be KQ positive over X. And this one here will be negative 2KQ over X. And when I add them up, I get negative KQ over X. And that's my electric potential at that location. And that makes sense. It's halfway between these two. It's closer. They're the same distance away, but this is a larger negative charge, so this should have a negative potential right here. All right, next question. Sketch the electric field strength on the axis below, assuming right is positive. Okay, so look in the center. See how it points to the left? We're going to get a negative electric field in that region. So our electric field should be negative down here. Another thing to notice is that the electric field is proportional to 1 over R squared. So as we get closer to the charges, we're going to hit an asymptote. So what we should get is a inverse that looks something like this for this one, and an inverse that looks something more like this over here. It should be a little farther away because it's twice the charge. And then on this side, the electric field, well, when I get really close to this charge, the green one will be bigger than the blue one, inverse squared. So it's going to be positive at some point to the right. The green one will win. but at some point over here it's going to cross over. And we'd have to calculate that to be sure where it's at, but we do know it's going to be to the right at the beginning when we're close to this plus x. Over here our electric field is definitely to the right because green is too small, so we're going to have an inverse square that's going to look something like that. So that's what our curve should look like. And then the electric potential will actually be easier. Electric potential is proportional to 1 over r. And so we should have asymptotes here again. But here we have a positive, so it's going to go like that and like this. And then over here we have a negative, so it should go like this and like this. And these should be a little farther away because they have twice the charge. And then somewhere here they're going to connect up. Now remember, we had a negative potential right here. So they're going to cross over somewhere over on this side, farther to the right. But here's another weird question that has shown up on the AP exam before. It says, 2 positive charges with isolines of constant potential are shown in the figure to the right over here. Discuss the relative magnitudes of the charges. Discuss the similarities and differences between this figure and that of 2 masses and their associated isolines of constant potential. So if these were 2 masses instead, what would be the similarities and differences of the isolines of constant potential, gravitational potential for the mass, and constant electrical potential for the charges? Okay, 2 positive charges have isolines as shown. So this is a positive and this is a positive. So that means that these isolines are going to be positive volts. And then they're going to decrease as we get farther away. Notice that they envelop here. And that this one, this is the same electric potential here all the way around. And then if we go in, it's less. It's going to be greater positive here, greater positive here, and then this one's even more positive and it's farther away. So since V is proportional to 1 over R, we must assume that this one is a bigger positive charge than the one on the left. All right, so that answers part A. Discuss the similarities and differences between this figure if it had 2 masses and its associated electric potential lines. So what if we had a small mass and a large mass? What would the isolines look like? Well, it would look very similar. In fact, it would look identical as long as this mass is bigger than this mass in the same ratio that these are. Except there's two major differences. Number one is this is going to be negative isolines because the gravitational field always points inward. Okay, so these electric field lines or field vectors are going to point outward. So we got that difference between the two. The gravitational field points inward, the electric field points outward, and so these are going to be large positive numbers for volts, and it's going to decrease. So like 100 volts, 90 volts, 80 volts, 70 volts. The opposite for G, little g, gravitational field. We have a large gravitational field here, but it's negative, and so this is going to decrease to more negative potential as we get closer. So the signs are different for our potential, and the electric field point in the opposite direction as the gravitational field. If these were negative charges, then this figure and this figure would be identical. Okay, here's number 10. I'd like for you to read this question, and then I want you to work it out on your own, and then we'll work it out together. We have a negative Coulomb, 2 Coulomb charge with a mass of 0.5 of a kilogram at this spot. So I'm going to put my negative charge right there. And then it says, how much work does it take to move the particle to point C? So we're going to move it from here to here. How we get there doesn't make any difference. It's still the same change in potential. So the work is going to equal the change in electric potential energy, which equals delta V times Q, which for us will be V final minus V initial times Q, which for us is 50 is our final, minus the original 70, times a charge of minus 2 coulombs. And if we put all that together, we get plus 40 joules of work. Nice. Okay, part B says now we move this thing from C to B. So we move it from here to here. And hey, it's on the same equipotential line, so there's no work. So for A and B, the work is 0 for B. Easy. Part C, what's the direction of the force on the particle when it's at point B? Well, it's a negative charge. And our electric field always points from more positive to more negative. So the electric field is in this direction to the left, and this is a negative charge, so it's going to get a force to the right. So our force is to the right. Part D says the particle is released from point B and travels to point A. So it goes back home to where it began. And it asks for what's the velocity of it. Well, we're going to have a change in electric potential energy. The negative change in electric potential energy, remember, equals the kinetic energy that it gains. And so this, we know, is going to be negative 40 joules. It's going to go down, but that's a negative change of that, all right, because it went up 40 joules going from here to here, so it's going to go down 40 joules, from here to here, and then we take the negative change of that. That equals 1/2 mv squared, which is 1/2 our mass is 0.5 v squared, and that's 40 joules. So V squared equals 160 meters squared per second squared. So V, of course, is the square root of that, which we all know is 12.6 meters per second, because we have calculators for brains. Okay, number 11 has another capacitor, and this one has numbers in it, but I'd like for you to work everything out in symbol form first before you plug in your numbers, because if you can't work it out in symbols, you'll never get the numbers right. So pause the video, work this one out, and then we'll work it out together. Number 11, we have a capacitor with a proton here in the center. It says, what's the direction of the electric field? Well, remember, the electric field always points from positive to negative, so our electric field is to the left. It says, calculate the electric field strength. Well, don't try to use any of those spherical geometry equations. We have to use the electric field equals delta V over delta R, and that's a delta V of 50 volts divided by a distance of 0.006 meters, which gives us 8,333 volts per meter, or if you prefer, 8,333 newtons per coulomb. It's the same thing. Part C says, calculate the force on the proton. Well, the electric force is equal to E times Q, and that's this E times the charge of a proton, which is little e. Remember that little e equals 1.6 times 10 to the negative 19th coulombs, which is on our equation sheet. When we plug all that stuff in, we get 1.33 times 10 to the negative 15 newtons, a very tiny force from this rather large electric field. That's because it's a tiny charge. D, sketch the path of the proton. Well, it's released from rest as far as I can tell, so it's going to just go straight to the left along this pathway here. That was easy. E, what is the acceleration of the proton? Well, more mechanics. Acceleration equals the electric force divided by the mass of the proton. Now, the mass of a proton is 1.67 times 10 to the negative 27 kilograms, but you don't have to remember that because it's also on our equation sheet. When I plug that mass in and this electric force in, we get an acceleration of 8.0 times 10 to the 11th meters per second squared. Now that's an impressive acceleration. No time to get to the speed of light, which we can't really do, but that's for later. Part F, what is the speed of the proton when it strikes the plate? Now, we could solve this two different ways. We could use kinematics with v squared equals v naught squared plus 2a x minus x naught, or we could use energy. And we could say that the 1/2 mv squared of our proton would have to equal the delta v times E. The change in electric potential energy would have to equal the gain in kinetic energy. Either one of these, it doesn't matter which one you choose, you're going to get the same answer of a prodigious velocity of 69,000 approximately meters per second when it travels from here across to here in a distance that's a ridiculously small amount. So protons and electrons, because they're so tiny, and the forces relative to their mass can be so large that they can get to enormous speeds in a very short period of time. And then G says, now assume the proton has velocity downward. When it's released, sketch the path. The force is to the left. If the velocity's down, it's going to be like a baseball. It's going to have a parabolic arc downward. And if it hits the plate, that's a parabola. Sorry, it's kind of messy. That's a parabola. Now, if it goes fast enough, it will exit out before it hits the plate. And so this top part here will be a parabola until it leaves. And then after that, it will just go straight, because an object in motion stays in motion when it doesn't have the electric force pushing down on it towards this plate anymore. So parabolic inside, linear outside. Question 12, we have two solid conducting spheres as shown in this figure. Sphere 1 initially has a charge of Q naught. Sphere 2 is uncharged. Sketch the electric field and electric potential for sphere 1, the charged one, on the axis below. So here's electric field and here's electric potential. Part B, the two spheres are brought briefly into contact. Boy, my English sucks. And then separated. Calculate the final charges on each sphere. All right, work this one out, and then we'll work it out together. Okay, sketch the electric field for sphere 1 and the electric potential. I'm going to draw a vertical line on both of these because there's going to be a different behavior inside and outside. On the outside, the electric field is kq over r squared, spherical geometry here. It's a 1 over r squared relationship. So that means when we double the radius, when we get out here 1 radius away farther, we should have only 1/4, because it's r squared, of the electric field. So it's going to look like this, really steep. Oops, I messed up. It's going to look like this, because we know that the electric field will be a certain amount on the surface. So I'm going to make that E naught on the surface. All right? It's asymptotic to 0, not the surface. That was my mistake. All right, inside, the electric field has to be 0 because it's in equilibrium. It's going to look like this. Our electric potential is going to be kq over r. That's a 1 over r relationship. So when I get twice the radius away, 1 radius, twice the radius, then I will have 1/2 of the potential we have on the surface. And then when I get 4 radii away, I'll have 1/4 of the electric potential. So we're lined up there, and so ours is not quite as steep of an inverse graph as we have over here. It's the 1 over r squared. And then the potential inside has to be the same. Remember, it's flat on the inside. So no forces on anything on the inside, and it has a plateau of potential, so any charges inside don't want to move one way or the other. The two spheres are brought briefly into contact, because my English is terrible. Calculate the final charges of each sphere after we touch them together. So when they touch, charge is going to flow until they have equilibrium. So our electrostatic equilibrium condition is that the voltage for sphere 1 plus the voltage, equals the voltage for sphere 2. That's our equilibrium condition. So that is K Q1 over radius for sphere 1 must equal K Q2 over 2R for radius 2 for the second sphere. So K's cancel, R's cancel, and I'm left with that Q2 equals twice Q1. So Q2, our sphere 2, is going to have twice the charge of sphere 1 at the end, which makes sense. It has more room. But how much exactly of the original? Well, our other condition is conservation of charge. This is huge. Q1 plus Q2 must equal the original Q0 that we started with. So if I plug this in for Q2, I get Q1 plus 2Q1 equals the original. So that means that Q1 will equal 1/3 of the original. Oops. And since Q2 has twice of Q1, that means Q2 will equal 2/3 of the original. And that makes total sense. Q2 is twice as big as Q1, and when add them together, we get Q0, the original charge. Genius. A positive charge is placed at point A, as you can see here, of this right triangle. So ABC right triangle. Two mystery charges are placed at points B and C. The force on the mystery charge at point C is shown right here. So this point C, whatever we put here, has a force to the left. What are the two mystery charges? So can you tell? Positive, negative, both the same, different? And then how do the magnitudes of the charges at points A and B compare, and explain how you know this? All right, lucky number 13, our very last electrostatics problem. Thank goodness. So here we go. We have a positive charge placed here, and then we have two mystery charges placed at C and B, but we know the force on C is to the left. So what are the two mystery charges? Well, let's just take a guess. What if this one's positive? Then this one would push it away, and if this one was positive, it would push it away. That won't work. So what if it's negative? Then that would pull it, and that won't work either. So that means this one can't be positive. It has to be negative. All right, so this positive and this negative, they'll attract with a force this way, force from A. And then B, I need another force added to this one to give us the final. So that means it has to be up and to the left, force B. So that means this one must be negative to give us a force up and to the left, and I ran out of room up here. Those are our two charges. Both of them are negative. All right, how do the magnitudes of charge on point A and point B compare? Well, we can see that F is proportional to KQQ over R squared, or in our case, Q over R squared. Now take a look. This force here is bigger. So the force from A is bigger, but it has a much bigger distance than B does to this charge. So therefore, charge A must be bigger than charge B. All right? So the plus charge has to be bigger than the negative charge at B. All right. We're done, everybody. All right, everybody. We're done. So that's static electricity. It's a huge, huge part of the AP Physics 2 exam. So I hope you learned well. And I hope you have hair like this young man. All right, bye-bye.